In this video, I'm going to show you how to create a new geometric function in one of your designs that might supplement the existing geometric functions in FullControl. I'm also going to show you a built-in function that I've created to do the same thing, but with a bit more functionality. And I'm going to show you how to take your function that you've written, save it as a gist, and then import it into any of your other designs. So now that function will be reusable. And make sure you share those designs with those gists and stuff with us, with the email addresses, or tagging us on social media. Email addresses are just at the bottom here, because they're going to be useful for us, useful for everyone. Somebody added an issue to the GitHub repo, which was to convert a single wall into multiple walls. So if you've got one single perimeter, how to convert that into lots of walls that are all offset correctly in the X and Y positions. So I've already opened the design template in this window and got it running, and I've created this very simple design with points, 5 points, which are then plotted. So you can see the direction is going from purple to light blue. So we're going to create an offset of those points going outwards by a set amount. So the way to do that, this is a sketch of it, and then we're going to look at each line individually. So first this line, and then basically calculate the line points, the start point and the end point, the direction of the line, the direction we want to offset, which is 90 degrees, and then the points of the offset line. So that's what we'll do in several steps, and then do that for this line, this line, and this line, and then finally figure out where these lines actually intersect using one of the built-in FullControl functions, and then those 4 points will give us the offset, the corner points of that offset path. So I'm going to do this incrementally in the design. The first 2 points are going to create a line. So line equals a list of 2 points, and that's going to be points 0 and points 1. And after I've done this sort of manually, I'm going to convert it into a for loop. The direction of that line, let's call it the line direction, is going to be, I'm going to use a FullControl function called point to polar, and that's going to basically say the target point, which is the end of the line, so line 1, relative to the origin point, which is the first point in the line 0, and then that's going to return an object with a radius and then an angle aspect. So I just want the angle aspect. And what I'm going to do is then print that just to check that it's what I expect. So that's an angle 2 through 5. Doesn't make much sense. So what I can do is math import radians and degrees, and I convert that to degrees. It's 135, and that's correct because we have in the X direction it's 0, so this is 135 degrees anti-clockwise from the X direction. So that's looking good. We then want the actual offset direction, which is very simple. That's going to be offset direction, line direction equals line direction plus 90 degrees. So now we've got our offset direction. We want to move this original line, so offset line. First we need to say how much we want to move it by. So let's call offset equals, I'm going to move it by a large amount so it's easy to see, 10. So offset line equals, I'm going to use the FullControl move command. We're going to move the line, and we're going to move it by a vector, which we haven't defined yet. So that vector is actually going to be this, based on this direction. So there's a function in FullControl called polar to vector. So if I create my vector here, polar to vector, and it's going to be the length and angle. So this is a polar length, polar angle. The length is going to be our offset, and the angle is going to be our offset direction in radians. So that vector should fit in there, and then we should get this offset line. So what I'll do then is just add that to the. We should see it appear down here somewhere. And there we go. So it's printed into 4 lines. It's then printed into there, which is because we've just added that point to the list of points and then printed that. So that's where I expect it to be. Then we want to do it for all the other 4 lines. So if we then put this all in a loop to happen multiple times, then we can say for in range and points. So for each point, we can do this stuff. Each point in our list of points. However, we don't want to do it for the last point because there isn't a point for it to go to. It's the last point, so there isn't a next point, like what we need to create a line. And we're going to sort of store our offset lines in memory because we need them. So offset lines, I'm going to create a blank array, a blank list, and then we'll append, instead of creating a variable, we'll append the newly created line to that list. So we'll get a list of newly created lines now. The only thing I need to change is make sure that instead of using the 0 and the 1 point, we use the I and then I plus 1. This will be fine. So that will hope to be fine. And then if we put offset lines in our path, this won't quite work at the moment because offset lines is a list of 2 points, a list of lists, and in FullControl, the list that you're printing needs to be a single 1D list. So I'll use the FC button function. We should see now those 4 lines being printed around. They're all connected because we've not told it to turn the extrusion off, so it's just moving from point to point. So that's got us most of the way there. We now just need to find these intersects. So if I get rid of that, the first 2 lines, we can say intersect equals, we need to import a function from FullControl Lab. And what we need for that is the 4 points of the line 1 point, first point, line 1 end point, line 2 start and end point. So we'll have line, we'll have offset line, let's say the 0th offset line and the first point of it, an offset line and the 0th offset line, the second point. And then we'll have exactly the same, but it's going to be for the offset line number 1. Together those last 2 points. So that should give us an intersection point. And what I'll just do is create the first one of them and check that it's actually coming down here. Okay, so it's not quite, and the reason I put that in square brackets is just a quick hack to make it add this to the points array. It's adding 2 arrays. So the first line is going here, the second line is going here, so it's actually going to that point first. We probably want it to go to this point first because that's the offset one of this one, but that's close to what we're after. We'll fix the sequence afterwards. So then we want to do that for all of the lines. So for I in the range of the offset lines. So for each offset line, but we don't want to do it for the last one because there's no offset line after it, and the principle of this is comparing the first line, the current line to the next. So this is going to be the ith line and then the I. And again, we want to put these into an array. So intersection points and each intersection point. So now let's have a quick preview of that. And that's looking quite good, except yeah, because this hasn't got the first point or the last point, because it's only looking at this line compared to that one compared to that one compared to that one. So a quick hack to make it consider those first and last points is to just put an imaginary line kind of before and after the list of lines. So if I've got my offset lines, and I can just, a quick way to kind of hack that is just to say we're going to have the final line first, plus all the other lines, plus the last line. That means we'll basically be getting, instead of what we previously had, which was line, 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 it's now going to go line, 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 line. And it's going to find the intersection points between this line and that line first, which will give us down here, and then go through this point, this point, this point, and then that point again. So that should hopefully work straight away. And what have we got here? So no intercept found. It's because I wanted to add the first line to the end of the list, not the last line. If you've got two parallel lines, you can't find an intersect between them. Okay, that's looking perfect. So then we can now potentially put this into a function. So we define our points and our offset, and we feed them into a function. Let's say the function is called offset path, and what we give it is the points offset, and what it will return is these list of intersection points. So then I'll say steps equals what that returns, and then I'll plot them. So let's create this function. I'm going to return the intersection points. So we're going to receive a list of points and the offset, and we will return the list. So this will hopefully work. So now we just got the offset one, which is looking good. I can also do the this list of steps is the initial points plus the offset points. That's good. And then this would clearly be quite easy to do, to put a for loop. So if offset was gradually increasing from 1 to 10, then we could put for I in range 11, so we'll go from 0 to 10, and then we'll have steps equals no, we'll go from, so we do steps equals points, and we'll append that steps extend offset points, and then if we have offset 0.5, offset times by 5. 1, so it starts with 1 when I is 0. So that should give us 10 lines plus the original line, 11 lines in total, all offset. And we got one problem there. Steps equals points. Let's so the problem was that I kind of was pointing to this points, and each time I was kind of increasing that variable rather than a copy of that variable. So now I've just slightly changed that. That's just a Python thing where if you say steps equals points, it just points steps to the original variable. So now that's all looking fine, except it has offset too much for the first one. So for I in range 10, that looks better. I don't know why that looks better. I thought there'd be a +1, but don't need to figure that out for this video. So that's given us a nice offset, and we could do this with some more complex geometry. If we did a say a polygon, instead of creating this list of points, we could say points equals fc.polygon y, and that's going to have a center of fc. Hexagon, and that's doing it. And perhaps if I want to make the function a bit more fancy, I could do something like add a flip option, defaulting to false, and if flip is set to be true, if flip, then we change the direction of the offset. Offset equals minus offset. So now it would be very easy to change the direction. So this is starting with the purple and ending, going inwards and ending with the blue. Whereas now, if I set flip equals true, it will start with the purple and end with blue outwards. So we can just decide what's useful to include in functions and what's useful to include in the design. So this one then, I could save this as a gist, which could then be imported. So if I copy this code and gist, and let's say this is offset path, I just got path dot pi. Put this in here. We don't need any of this bit. We just want to return the intersection points. So it's going to import these assets. It would also need FullControl. And then it should hopefully work. So if I create a secret gist for that, then that's got an address, and I've created, there's a little sort of bit of code can be used to actually then import that function. So if that function in my gist is called, let's change its name slightly just to check that it's work. Set path gist. Then in here, what I can do if I create a new code cell, and the gist URL is going to be what I copy from here. The module name is offsetPath.py, and the function name is offsetGist. And if I run that, I should have a function called offsetPathGist. Create a new code cell just with these bits. So an offset path gist, and then that will hopefully give us what we want. And there we go. So you could now access that function in all of your different designs by just downloading it directly from the gist. Of course, if you're working locally, then you just need to save the Python file, and you can import it from the same directory, or however you want to set up your importing. But if you save a Python file, just like this gist Python file, in the same directory as your notebook file, then you'll be able to import it directly from there. So that's the creating a little function to do offsetting of paths. I did create an inbuilt one, so you don't have to do this yourself, which is demonstrated in the lab geometry tutorial. So if I run this again, it's this offset a path section, and it's got a few extra options than what we showed there. So it doesn't need to be a closed path. You can have an open path, and it will just offset the ends of that path perpendicular to the direction of those lines. If it is a closed path, it will automatically detect that. And then you can actually set the number of repeats and the number, whether it's inside or outside. And you can see here that it's actually traveling between those repeats rather than just by default printing between them. And that's, you can set that in when you're calling the offset path function, whether it's traveling or whatnot. And you can also include the original path in that, return it the original path and the repeats. And then another useful thing is this applying a radius. So this becomes really useful if you have very acute paths. So if I change this y to be, say, 100, regenerate this, and you'll see that looks relatively neat and logical. If we didn't have the arcs on the corners, and it's a really extended corner that you get, and there's gonna be some gaps there almost certainly as you're printing up and down those bits. So that's quite useful, but it only works on the outer edges, because if you imagine printing this outside edge first and then trying to put an arc in here, it's not going to help matters. It's only going to make things worse. So you might want to define inner edge and then print outside that rather than the other way around if you want to add this nice radius. So that's there. It's in the lab, so you have to import it with from the lab. It's just in the lab at the moment because there might be some bugs in it because it's quite new. But it's a very easy import statement. Just as you'd normally do, import FullControl as FC, you just import lab.FullControl as FC lab. That's already built in when you install FullControl. And this lab geometry Colab notebook is there in the tutorials. You see it at the bottom here, FullControl lab geometry. And that's it. There's another thing slightly relevant is this is the method of doing a similar thing, multiple walls, but instead of defining one and then having the other lines repeat out from it at an equal distance, this one you define the outer wall and inner wall and how many lines you want to fill in between those walls, and then it will automatically calculate where those lines need to go, what their widths need to be at all the different points. And if you set vary speed as true, then it will slow down when the extrusion is wider to make sure that the volumetric flow rate is constant, which is really valuable for say Bowden systems or for less rigid polymers, and that's all linked to journal of paper which you can download for free. Very similar to what was shown in Arachne Cura, but this was done entirely separately and in a quite a different way. And the journal paper explains the kind of strengths and weaknesses. So this is quite complicated. The maths behind this is really complicated, but hopefully this function is kind of usable without needing to know any of that maths. But it's in the lab because it might not be that easy to use right now. So if you have any requests for new features, new functions, or you just want to give us some feedback, then make sure you put some comments in the issue section of the GitHub repo.